Okay, can you see my slides?
Yes.
Okay, great. So the title of the presentation is Quantized Approximate Signal Processing Towards Homomorphic Encryption for Audio. I will progress like this. First, I will introduce why we are doing such a study. Then I will describe the full methodologies. And then we have a large experimental setups with different scenarios that are useful to encrypt audio data. I will not present everything in our paper. It's an archive paper right now. It's still under review. For the context, speech is a very sensitive data. Of course, everyone knows it, especially in healthcare application where we want to potentially have give back information to doctors, but we don't want anyone in the middle getting other information based on speech, because it's very well known that we can get the sex, the gender, where the person comes from, easily based on audio, even the Mel filter bank or any time frequency representation. And as we are doing computing, we need to have the data in clear. And the goal of this study is to have an end-to-end audio processing pipeline for different use case scenario. In our case, I want to underline the fact that we want really an end-to-end, like very from scratch. There are other approaches that have worked on this topic. Of course, there are other privacy-preserving methods, but at different stages of machine learning processes. We are mostly interested in inference, so the models and the pipeline is already trained and set up. But in our case, we want to have a model which is end-to-end. So we are collecting the data with the microphone, and we want to encrypt it right away, which is quite different from what has been done with homomorphic encryption and audio or speech. People compute audio features and then encrypt these audio features to have a specific application, such as detecting Parkinson's disease or detecting classifying the sex of the individual. And our goal is to, do you see my mouse?
Yes, we can see your mouse.
And our goal is to have, thank you. The goal is to have really an end-to-end pipeline where we go from the raw waveform, we encrypt it, and we go up to the prediction. But it entails that we have to compute a time frequency representation in a private manner that is fed then to obtain different things. We can have directly the time frequency representation. We can have audio markers, which are very important in healthcare. So for instance, it's very well known that in Parkinson's disease, you have prosody effects. So people measure the standard deviation of the fundamental frequency. So it's important to capture well this marker and to keep it accurate in a private manner. And of course, we want also directly machine learning prediction. So why quantized approximate signal processing? In our paper, we have a different set of contribution. We compute in a private manner different set of time frequency representation, Mel filter bank, MFCC, gammatones. And we propose enhancements of this time frequency representation that are constrained by using homomorphic encryption. And then we propose a large framework for evaluation of these privacy-preserving toolkits based on statistical analysis and also machine learning evaluation. And of course, we have experimental results to showcase everything. A little bit of background concerning fully homomorphic encryption. The goal is to make computation based on already encrypted data. So we can maintain the encryption of outputs while the input is still encrypted. And fully homomorphic encryption, the goal is to have the exact computation in this domain which is encrypted. So we want the equivalence between a computation done in encrypted data and not. We want to preserve the exact computation of this function. What's happening in terms of network and servers? An encryption is done on the client side, which is sent, for instance, to Calliope or any other external server, which has a function f hat, that is apply to this encrypted data. This encrypted data can still now transit to the client, to another client, and then this person can decrypt this information and have the output, which is important, for instance, for a clinical application. Now, a little bit of our goal. If we have to dive in terms of what we want to do, we have a waveform, which we denote by X. We have a time frequency operator that can be short for time Fourier transform, MFCC, gammatones. And usually for speech application, we have an additional function G that is going to compute over this time frequency representation a specific marker or directly ML function. So actually, the goal of this project is to compute the more accurate manner this T of the time frequency representation and to have an equivalence in the encrypted domain, to not lose any information and to maintain this performance. However, in our case, we choose to use an encryption scheme over the torus, and numbers are represented as integers. So we have, I know there are different choices that can be made. So for instance, with CKKS, but in our case, it was very convenient, and we will talk about it later on, why we did that. So we need to compute our circuits of computation, and then also quantize these models, but also the inputs and each output. And then at the end, there is a translation of this quantized circuit into a secure secure computation that can be done with this encryption scheme. So there is a lot of work actually to not lose information at this first step of quantization. Actually, no, the compilation is not losing much information, and most of the work should be focused if we use this encryption scheme in this first quantization step. A little bit of background of range-based. The quantization is, in our case, is range-based affine uniform quantization, and we have data to quantize this continuous data, and we can dequantize after that with some hyperparameters. What we need to do, so here, the transformation in a quantized circuit can only be done with, as we want a full circuit in encryption domain, we need to have from scratch the raw waveform, the time frequency representation, and also the G function, which is in a PyTorch function. So we cast it's been done to speed up the Mel-filterbank short-term Fourier transform as a convolutional network. Actually, we can reformulate the short-term Fourier transform as a convolution with weights and specific windows. It has been done in many toolkits to have that in PyTorch. So we re-exploit this to have that in our framework to compute the Mel-filterbank, gammatone, MFCC that can be transformed in a quantized manner. So we can recast the usual convolutional spectrogram. But as I said, if we quantize naively all the inputs, and also all the weights and all the operation, we can lose a lot of information. So most of our work has been done to reduce the amount of computation during the inference of this short-term Fourier transform. In our experiment, we found out that most of the loss is done in the time frequency representation. The first step looks like this. And so we propose a number of methods along the way. So if we want to have this short-time Fourier transform in a quantized approximate spectrogram, actually, the waveform needs to be quantized. The output of the AND window as a weight convolution needs to be quantized. Then even all the operation. And what you see in red is proposals on our side to change the classic short-time Fourier transform and also next step to have a cheaper short-time Fourier transform, but not lose information for the end goal application. I'm going to present there are a large number of hyperparameters that need to be tuned. And actually, we are using training data to find the best hyperparameters for quantization, which where do we want to put a lot of budget, because we have with this quantization and compiler in fully homomorphic encryption, we have a limit of number of bits and operation that you can perform at the time of our paper. It's progressing fast, but in our case, we have a budget that is limited at each step. So we have to do we have to reduce the budget for each operation. I'm going to present the two main the two methods that have shown the best results. So first, basically in signal processing, we can as we are casting the short time Fourier transform as a convolution, we propose to use dilation in the convolution to not use all the input signal. We subsample basically the convolution and to not use the full input to compute, for instance, one specific time frequency representation. In our paper, we demonstrated the theoretical error that is being injected and the other time frequency injection in other frequency beams that happens when we do dilations. So for instance, dilation factor 2 in 2D looks like this. So basically, we are subsampling the input. Is it okay so far? Okay, I assume.
Thank you. Yes.
Then we have another method to reduce the quantization parameter for the convolution. Actually, we can see the time frequency representation in a complex domain, and where we have on the unit circle in the complex domain. So we can actually reduce the precision of this different time frequency projection of our input signal. So what we propose, it has been proposed a long time ago to speed up short-time Fourier transform without multiplication. And actually, it was very useful in our case also to use this poor man's projection, basically the different time frequency projection along the wave of each time frequency beams can be casted as along a quantized short-time Fourier transform coefficient. So we have less weights possible along the way. So as a reminder, our goal is so we have this time frequency computation, and then at the end we can add a network or compute some markers on top of time frequency representation for different applications. So we are making approximation basically between this G0T of the inputs, and we are losing some information along the way due to quantization and our approximation. And our goal actually is to maintain the accuracy, for instance, for machine learning classification, or the accuracy of the audio markers, for instance, for health application. I'm going to show some of the experiments. First, we validated in our paper just the absolute loss between the time frequency representation and the one performed in the clear domain. Then we validated the audio markers in absolute value, and then we tackled some classification task on one specific dataset for emotion and sex classification. We use two datasets that have a large variation in terms of vocal exercise, women, men, and also type of human vocalization. And for all experiments, as we are optimizing for the quantization bit widths to obtain the best circuits, we have, of course, a calibration set and a test set, and I'm only showing the results on the test set. For instance, what are important audio marker or time frequency representation? We all can talk about short Fourier. I'm going to show you some short-term Fourier transform, Mel-filterbank, MFCC gammatones. And for audio markers, we computed a number of audio markers, such as the mean over frequencies of a Mel-filterbank, or the root mean square energy, such as this. So we compute the root mean square energy and statistics of this root mean square energy, which can be useful, for instance, for emotion or for some vocalization type classification. And then at the end, we use a simple CNN based on the time frequency representation to classify between gender and vocal exercise. I use in our case, it was gender, even though I mentioned sex before, but it was a gender classification in our case. So as I said, on the full process, we compare the approximate output and we compare to the exact output. And we are not using the calibration data. You can look in our paper the full methodology if you are interested. And we are optimizing actually the bit weights parameter in the full circuits, and we try to allocate in the best position where we should put the most precision along the way. The parameter are here for the input and output of each operators, and also in the weights of each models, of each convolution or activation function. Yeah, that's what I said. And the criteria is either to reduce how to optimize on the stratified, on the calibration set, we reduce the distance between the reference spectrogram, or we optimize for the best audio markers on the calibration sets. Actually, visually, we lose a lot of information when you can see on the top the original audio data for a normal speech sentence. For the different input, for the different time frequency representation, and when we look at them in the quantized secure time frequency representation, we decoded them and we can show them also. And what we see is we are losing a lot of high frequency representation, mainly due to the high values in the low frequency and the high variation in the low frequencies. It's left for future work to improve different range-based affine transformation for each frequency band, for instance. But even with this kind of representation, we can still do some work. For instance, we did a statistical analysis. What this slide is saying, we want to evaluate if we are making, so for instance, we want to evaluate the mean standard, the mean values of the frequencies for Parkinson's disease versus healthy controls. And usually it's separate the two classes. And so if the compute in the secure manner is done properly, we're going to make the same conclusion on the same difference between the two classes. So for instance, if I compare two groups, I'm going to take the same decision if it's in a clear manner or private manner. And so basically we run a lot of statistical evaluation on the many classes of our datasets based on sex, gender, vocal exercise, and we can count the number of true positive. Fully homomorphic encryption preserves the separation of classes. We can make false negative. We lose the separation of classes. We can preserve the non-separation of classes. And inversely, we can create a separation that doesn't exist in the clear manner. What does it mean? For one specific audio marker, we have like a lot of experiments that can be done across our dataset. We can run many experiments. So each point that you see on the left is one statistical analysis that is performed. And basically, we want to increase the number of experiments that are in the green tiles. And otherwise, it's false negative or false positive. So for instance, the mean gammatone standard deviation between these two vocal exercises, in the clear manner, they were separated, but in the fully homomorphic, they were not anymore. And so basically, we discriminate between our method with the error rate, with the false positive and false negative against all the statistical analysis we made. And what we noticed is already the convolutional STFT that we proposed with the neural network was were making mistakes, but not all the time. Around 10%, for instance, for gammatone, but we found that, for instance, for root mean square, the error were quite low. And what we found is that the Pullman and the dilation approximation that were introduced were improving our results for instance, the VocalSet dataset. We found similar results in the other datasets, OxVoc datasets, where we found that also two different parameters of the dilation could be useful. On the other hand, there were methods that we thought would have helped a lot, and they degraded completely the performance, such as cropping windows or adapting the window based on the frequency. At the end, it's nice to preserve statistical differences between groups, but we are in speech community. Most of the applications are interested at the individual prediction based on one single speech, and we are making machine learning prediction directly with fully homomorphic encryption. So what we noticed is actually even with the low frequency in this one data set, to go with a small CNN, the accuracy was almost, there was of course a train and test set, but the accuracy of this network was around 90%, and the results were varying with the short-time Fourier transform versus MFCC. But what we found is the fully homomorphic version was not degrading that much the performance. This is the same slide, sorry. And what we did also is to look at all the calibration optimization we made, and we wanted to understand where the budget was allocated when we were optimizing this quantized circuit. And what we found is the best combination, but more bits on activation and less on convolution weights. So to reduce, we can reduce the budget actually on the weights of the convolution, so the short time Fourier transform, the ondulation, which is logical with what we found based on the Pullman quantization. And we have to preserve as much as possible the budget on the input and output, on the input of each of the audio transform and each different layers. So to conclude, we have three results. It was possible to compute time frequency representation, audio marker, and to perform classification in a secure end-to-end manner. There were some attempts in the past, but it was not done end-to-end. What we found is that the dilation and Pullman approximation improve performance consistently for audio markers and also for classification. And what we found is also it's important to put more bits of activation on input and output of networks and less on weights. In the future, we want to think about the quantization schema based on the frequency. As I show you, we lost completely the high frequency representation. We want to test also different architectures. Can we think of architecture that are specific for fully homomorphic encryption? Can we think not like apply in a classic manner architecture to this application? And we want to think a bit more about the budget, where to put budget on the quantization schema. And thank you very much for your attention. Happy to take any question. I went a bit fast, but
Yes.